Welcome to the world of distributed systems, where we are often sold a beautiful dream, eventual consistency. It sounds so poetic, doesn't it? Like your data is just taking a scenic route and will arrive exactly when it needs to. But in reality, eventual consistency is often the industry's way of saying your system is technically broken for an undefined period of time. When we scale systems across the globe, we run into the speed of light. Information can't travel instantly. To keep our apps fast, we replicate data across multiple servers. But here's the catch. Keeping all those copies identical at the same time is incredibly hard. So architects made a trade-off. They promised that if no new updates are made, eventually all accesses will return the last updated value. But eventually is a very dangerous word in engineering, because it provides no guarantee of when that happens. To understand the lie, we have to look at the CAP theorem. CAP stands for consistency, availability, and partition tolerance. The theorem states that in a distributed system, you can only pick two. Since network partitions are an inevitable reality of hardware, we are forced to choose between consistency and availability. If you choose availability, your system stays up even when nodes can't talk to each other. This is where eventual consistency lives. It's a marketing-friendly way of saying we chose availability, so we are going to serve you stale data and hope for the best. Developers often treat this like a minor detail, but it fundamentally changes how users interact with your application. Imagine a bank balance that shows $100 after you just withdrew $50. That's not a trade-off. That's a bug in the eyes of the user.
One of the most frustrating manifestations of the SLI is the violation of read your rights consistency. You post a comment on a social media site, the page refreshes, and it's gone. You post it again, thinking it failed. Now there are two. This happens because your write went to node A, but your refresh read from node B, which hasn't seen the update yet. It feels like the system is gaslighting you. To fix this, you need sticky sessions or complex routing, which adds the very latency you were trying to avoid by choosing eventual consistency in the first place. You end up building a consistency layer on top of an inconsistent database, effectively reinventing the wheel, but with more moving parts and more ways for things to break during a failover.
Then there's the nightmare of monotonous reads. Imagine you are scrolling through a timeline. You see a post from 5 minutes ago. You refresh, and suddenly the latest post is from 10 minutes ago. Time has literally moved backwards because your request hit a replica that is further behind in the replication log. This isn't just a visual glitch. For automated systems like inventory management or financial trading, this time travel can cause catastrophic logic failures. If a system thinks the stock price is 100, then 105, then 100 again, it might trigger sell orders that shouldn't exist. Eventual consistency assumes that as long as things settle eventually, the journey doesn't matter. But in software, the sequence of states is often just as important as the final destination.
This is where two people update the same piece of data at the same time on different nodes. This is where the eventual part gets messy. Most systems use a strategy called last write wins, or LWW. It sounds simple, but it's a silent data killer. Because clocks across different servers are never perfectly synchronized, the last write is determined by whichever server had a slightly faster clock. You could spend an hour writing a brilliant document, and I could spend 1 second fixing a typo. If my server's clock is ahead of yours, your hour of work is deleted forever, replaced by my typo fix. The system is consistent eventually, yes, but it achieved that consistency by throwing your data in the trash. This is the dark side of conflict resolution that marketing brochures never mention.
To solve these issues, researchers developed complex tools like vector clocks and CRDTs, conflict-free replicated data types. These are mathematical marvels that allow data to be merged without losing information. But here is the catch. They are incredibly difficult to implement correctly, and they come with a massive storage overhead. Your simple integer counter suddenly needs to store a history of every node that ever touched it. This is the hidden tax of eventual consistency. You start with a simple distributed database to avoid the complexity of ACID transactions, but you end up needing a PhD in distributed systems just to make sure you don't lose user data. The simplicity was a lie.
The complexity just moved from the database engine into your application code and your data structures.
So why do we keep using it? Because for some things, it works perfectly. If you are liking a video on YouTube, it doesn't matter if the count is 1.2 million or 1.2 million and one for a few seconds. High availability is more important than perfect accuracy for social metrics. The lie isn't that eventual consistency exists. The lie is that it's a one-size-fits-all solution for modern scaling. Many developers adopt it by default because that's what big tech does, without realizing that big tech spends thousands of engineering hours mitigating the side effects. If your application handles money, medical records, or critical state, eventual consistency is not your friend. You need strong consistency, and you need to be willing to pay the latency price for it.